It is good to welcome you to the lecture on convolutional neural networks for classification in R. And this lecture is going to consist of a discussion of a network, a convolutional neural network, for the classification of images of cats and dogs. So the first step is to obtain the data set, which is available on Kaggle for free. All you have to do is do a relatively quick registration, and then you can access the data. In this training set right here. The data itself is, as discussed, images of cats as well as images of dogs. So let's discuss the code now and how it solves the problem. The first portion of the code that you see here takes the large training set, this one that you would be downloading from Kaggle if you were to work through this example, and then takes a small portion for the interest of time and divides it into three subsets. These are training, testing, and validation. So up to here, it is simply code to set the data conveniently for us. Next, we load Keras, specify the shape of the input, which is 180 by 180, and 3 here corresponds to the 3 colors, as opposed to, for instance, grayscale. Now, this is not to say that the actual images are 180 by 180. In fact, they are of a diverse size and shape. For example, you can see this is certainly not 180 by 180. It is a rectangle, which is not a square in this case. But nonetheless, we specify that the model should expect this size, and later on we will reshape the images to this size. We take these inputs, we scale the layers, so it is currently taking values from 0 to 256, and then we're going to rescale that to 0 to 1. We could say this is still in the pre-processing stages. And now finally we define our first convolutional layer, followed by max pooling, and we repeat this several layers deep until finally we have just a number being output, which will be a probability. And then we create this model, and we can look at it in terms of the shapes and numbers of parameters. So begin with 180 by 180 by 3. Rescaling does not change shape. Convolution, etc., etc., until we reach the output, which is a single number. And we can see number of parameters, which can be relevant if we are thinking about complexity, amount of computation, generalizability, and so on and so forth. Compile the model with standard, loss, optimizer, and metric. And then we ingest the data, the images, and here you can see image size and batch size. We can specify some callbacks, and callbacks are when an action is made during the training. So for instance, save best only is to say that even though we are going to go through many phases of the training, and more precisely 30 epochs, only the best model will be saved, where we will be monitoring the validation loss. So in other words, only the best model in terms of validation loss is saved, and the rest are discarded. Callbacks are extremely useful for battling overfitting, because you simply specify a large number of epochs, and using the callback, you can stop when the performance is best, rather than keep going and degrading the performance. So I've run this model. It takes a bit of time to train, so I've skipped this step for your benefit and plotted the performance of the training. So you can see it starts off at about accuracy 50%, which is what we would expect from an untrained model with two choices, cat or dog. And as you can see, as we progress through the epochs, the training performance becomes much better. In fact, we might say that it has mastered all the data. But keeping in mind the validation, which is its performance on data yet unseen, we can see it is at about 75%. So this gap indicates that it has probably memorized the data, in other words, overfit. And we should probably be stopping somewhere here where the validation accuracy is highest. Finally, we can check the performance on the test set, which was not used as part of the training, only the training and validation sets were, and we can see it is about 70%, which is good performance given that we have only used a tiny fraction of the data, and that we are doing this primarily as an instructive neural network. So in summary, you can see that the code is pretty simple. At a high level, subdivide the data into three sets: training, validation, testing. Training is used for training, validation is used to check the progress of the training, and testing is finally used at the end to see how the model is performing. We define our convolutional neural network consisting of layers of convolution and pooling and the bookend layers. We specify how we want the optimization to proceed, ingest the data, and train. And finally, analyze the output of the performance graph to understand how we did and what we should do next. For instance, since we have been overfitting, we might think about a simpler neural network, or a greater variation of data, or perhaps adding in some dropout layers to combat the overfitting that has been occurring at the very end of the training.